So, good morning, everyone. Today we are going to discuss about the high pass RC circuit for ramp input signal. That means whenever we can apply a ramp input signal to the high pass RC circuit, what is the response produced by the circuit? And it's a mathematical expression. Now, this is the ramp input signal which is going to apply to the high pass RC circuit. So, we already know that the ramp signal is mathematically defined as its value is 0 for t less than 0. Is it correct? Now its value is 0 for t less than 0 and its value is alpha t for t greater than 0. Its value is alpha t for t greater than 0. And now it is applied to the high pass RC circuit. Vi represents the input signal and V naught represents the output signal and RC acts as a capacitor circuit. Now this is the corresponding response produced by the circuit. Now coming to the operation of the circuit is divided into two cases. The first case is when the input signal value is 0, that is at t less than or is equal to 0. Second case when the input signal value is greater than 0. When the input signal value is greater than 0. There are two cases. First case t less than or is equal to 0. Second case for t greater than 0. So it is observed that when the input signal is 0, that means for t less than or is equal to 0, that is case 1. Whenever you can apply this signal to the high pass RC circuit, whenever you can apply this circuit to the high pass RC circuit, what happened initially, we can assume that there is no voltage across the capacitor. Initially, we can assume that there is no voltage across the capacitor. That means the voltage across the capacitor is equal to 0 and we are applying 0 as an input signal. Therefore, the capacitor does not responded for the input signal because of the 0 input signal. That means the voltage across the capacitor is 0 and the voltage across the resistor is also equal to 0. Therefore, finally, the output voltage V0 is equal to Vi. That means 0 volts. That means for t less than or is equal to 0, the output response is equal to the 0 volts. Now coming to the second case, in the second case, that is for t greater than 0, the input signal increases linearly. The input signal increases linearly. That linearly increasing input signal is applied to the input of high pass RC circuit. Because of the linearly increasing input signal that is applied to the capacitor starts charging from its initial value, and the capacitor charges is in exponential motion, and there is a flow of current because of the charging through the resistor R. So because of this current, some voltage is developed across this resistor. Because of this current, some voltage is developed across this resistor. That voltage is nothing but V0. That means if the input signal increases linearly, the voltage developed across the capacitor also increases exponentially, and the output voltage also increases exponentially. That is clearly depicted here. Represented here. This exponentially increasing signal represents the output response. This linearly increasing signal represents the input signal. Now, it is observed that we say that the output response increases exponentially. Now we are going to derive the mathematical expression for this exponential response. Now, coming to the derivation, now we already know that Vi of t is equal to alpha t for t greater than 0. Now apply Laplace transform to this equation. That means alpha t. Therefore, Vi of S, that is equal to alpha by S square. We know that Laplace transform of t, that is equal to 1 by S square. Therefore, alpha by S square, that is represented with equation number 2. That is represented with equation number 2. Now, next consider the general expression for high pass RC circuit, that is Vi is equal to 1 by C into integral of I dt plus I into R. This equation represents the general expression for high pass RC circuit. In this equation, VR represents, that means this I into R represents the output voltage, because we are taking the output voltage across the resistor. The voltage across the resistor is represented with I into R, that is V naught. Therefore, I is equal to V naught by R. From this, we can also write as I is equal to V by R, V naught by R. Now, substitute these two conditions into this equation. Substitute these two conditions into that equation. If you substitute those two conditions, into this equation, this one. Therefore, Vi is equal to 1 by C into integral of, what is the value of I? V naught by R. So, substitute I with V naught by R dt plus I into R is equal to V naught. That is equation number 3. Now, from the input signal, we know that Vi is equal to alpha t because it is a ramp signal. Therefore, Vi is equal to alpha t in equation number 3. That is equal to R is constant, come to outside of the integral, that is 1 by RC into integral of V naught dt plus V naught. Now, apply Laplace transform to this equation. Apply Laplace transform to this equation. So, whenever you can apply Laplace transform, it is observed that here alpha is the constant. Laplace transform of t is equal to 1 by S square. Therefore, alpha by S square, that is equal to 1 by RC. Here it is 1 by RC is constant. 1 by RC into Laplace transform of integral of V naught dt, that is equal to V naught of S by S plus Laplace transform of V naught, that is equal to V naught of S. Therefore, alpha by S square, that is equal to, here V naught of S is there, here V naught of S is there. Therefore, V naught of S by S into S plus 1 by RC. V naught of S by S is taken as constant. Therefore, here there is no S term. That means S plus, here 1 by RC. S plus 1 by RC. So, here 1S and a square cancel. Therefore, V naught of S is equal to alpha by, move this one to left side. V naught of S is equal to alpha by S into S plus 1 by RC. Now, this is the expression for V naught of S. Now apply partial fractions to the equation V naught of S. So, whenever you can apply partial fractions to that equation, it can be written as V naught of S is equal to A by S plus B by S plus 1 by RC. A by S plus B by S plus 1 by RC. Therefore, alpha is equal to A into S plus 1 by RC plus B into S. Alpha is equal to A into S plus 1 by RC plus B into S. Therefore, if S is equal to 0, to solve this equation, two conditions need to apply. That means if S is 0, you get the value of A. If S is equal to minus 1 by RC, you get the value of B. Now consider the first case, that is when S is 0. When S is 0, we know that the term, bth term is 0. The remaining can be written as alpha is equal to A into S is 0. That means 1 by RC, A by RC. Therefore, A is equal to alpha into RC. We get the value of A in equation 4. Similarly, to get the value of B, put S is equal to minus 1 by RC. Therefore, whenever you can use minus 1 by RC here, the eighth term is 0 and the remaining is written as alpha is equal to B into minus 1 by RC. Therefore, B is equal to minus alpha into RC. So, we get the value of B in equation 4. Now, substitute the values of A and B into that V naught of S. Therefore, V naught of S is equal to A, that is minus alpha RC by S, plus B. What is B? Minus alpha RC by S plus 1 by RC. Now, V naught of S is equal, here alpha RC common, here alpha RC common, take alpha RC common in both terms. Therefore, alpha RC into, here it is 1 by S minus, here it is 1 by S plus 1 by RC. Now, apply inverse Laplace transform to this equation. So, whenever you can apply inverse Laplace transform, V naught of S is represented with V naught of T, that is equal to alpha into RC is common into 1 by S. Inverse Laplace transform of 1 by S is 1 minus inverse Laplace transform of 1 by S plus 1 by RC is e power minus T by RC. Therefore, alpha by RC that is equal to alpha by RC that is equal to alpha by RC into 1 minus expand this term. Expand this e power minus T by RC term. Therefore, 1 minus e power minus RT is 1 minus T by RC plus T square by 2 R square C square minus T cube by 6 R cube C cube plus and so on. 1 minus T by RC plus T square by 2 R square C square minus T cube by 6 R cube C cube plus and so on. Therefore, expand that term. That means take minus this minus 2 inside. So therefore, plus 1 minus 1 cancel, minus into minus plus, minus into plus minus, minus into minus plus. Therefore, you get V naught of T is equal to, take minus term to inside, V naught of T is equal to alpha RC into plus 1 minus 1 cancel. Therefore, minus into minus plus T by RC minus into plus minus T square by 6 2 R square C square minus into minus plus T cube by 6 R cube C cube minus into plus minus and so on. Therefore, V naught of T is equal to alpha RC by, take T by RC as common in all the terms. T by RC is taken as term constant in all the terms. So, the remaining can be written as 1 minus 1 T by RC goes outside. Therefore, T by 2 RC plus T square by 6 RC C square minus and so on. So, here RC common. The remaining term can be written as V naught of T is equal to alpha T into 1 minus T by 2 RC. Neglect all the higher order terms. Neglect all the higher order terms. If you get alpha T, that is equal to 1 by 1 minus T by 2 RC. Coming to the next part, that is calculation of transmission error. So remember these two equations, V naught value and Vi value, these two are required during the calculation of transmission error. Vi of T is alpha T and V naught of T is equal to alpha T into 1 minus T by 2 RC. These two are required in the transmission error calculation. So Vt is equal to Vi, that is alpha T minus V naught, that is alpha T into 1 minus T by 2 RC whole by Vi. What is Vi? Alpha T. So here one alpha T term, here one alpha T term, here one alpha T term. So take alpha T as common in numerator and cancel the alpha T and alpha T. Is it understand? Okay, so here alpha T minus alpha T into 1 minus T by 2 RC plus T square by 6 R square C square minus and so on by alpha T. This alpha T cancel. Here plus 1, minus 1, cancel. Minus into minus plus t by 2 RC, minus into plus minus t square by 6 r square c square plus and so on. At the particular time interval t, at the particular time interval t, up to the particular time interval t, the transmission error is equal to, substitute the value of small t with capital T. Therefore, t by 2 RC minus t square by 6 RC v square plus and so on. So therefore, from this, the transmission, the value of RC is far greater than t, then all the higher order terms are neglected and removed. Therefore, ET transmission error is equal to T by 2 RC. That means from this equation, it is concluded that the transmission error is directly proportional to the time period of the input signal, and it is inversely proportional to the resistor and capacitor values used in the circuit. Therefore, it is clearly observed in the response of the high pass RC circuit. What we know the value of transmission error. So this represents the transmission error. The deviation between input and output is represented by a parameter. That parameter is called as a transmission error. If this transmission error is directly proportional to the time period of the input signal, and it is inversely proportional to the resistor and the capacitor values used in the circuit. So that is about the response of high pass RC circuit for ramp input signal. Now briefly we discuss about first we consider the ramp input signal. Next we draw the high pass RC circuit. Next, by using two cases of operation. First case is t less than or is equal to 0. Second case is t greater than 0. Next case is t greater than 0. So for these two cases, we discussed the operation and we plot the response of the high pass RC circuit for ramp input signal for two cases. Now during the derivation part, first we write the expression for ramp input signal, that is as equation 1. Then we applied a Laplace transform to the ramp input signal, that is written as equation 2. Next we consider the expression for general expression for high pass RC circuit. In that high pass RC circuit, substitute the value of I, we can get equation number 3. Now we know the value of input signal Vi, that is alpha t, that going to substitute that value in equation number 3. Next apply inverse Laplace transform to the equation. There is an equation is obtained, and by using partial fractions expansion model, simplify this equation and calculate the values of A and B and substitute in that and apply, you can get this equation. After that, apply inverse Laplace transform to that equation, you can get this equation, and simply if you simplify this equation, you can get the response of high pass RC circuit for ramp input signal mathematically. Then calculate the transmission error. First define the basic definition of transmission error. Then substitute the value of Vi and V0 into the transmission error. Then by simplifying that expression, you can get the expression for transmission error and give a conclusion based on the equation of transmission error. That means the transmission error is directly proportional to the time period of the input signal, and it is inversely proportional to the resistor and capacitor used in the circuit. If RC is very low, the transmission error is larger. If RC is very high, the transmission error is low. Similarly, if the time period is high, the transmission error is also high. If the time period is low, the transmission error is also low. So those are the conclusions of this topic. So thank you so much for your patient listening. Thank you everyone for your successful cooperation.